So, now I will be talking about the first fundamental form of a surface. First fundamental form. Of a surface. So, we assume that a surface in parametric form is given to us. U1, U2 are the parameter of a surface. So, it will look like this in R3. What I will be doing, I will consider a curve over it. So, let C be a curve drawn over a surface. So, a curve C on the surface sigma will have parametric representation as U1 equal to U1t. U1 will become a function of a single parameter t, and U2 is also a function of the same parameter t. Okay. U1, U2 are varying over the rectangle, and U1 as well as U2 becomes function of another single parameter t, then this will give rise a curve. As you do in case of a plane, if the two coordinate x and y becomes a function of a single parameter, then xt, yt will give you a curve here. Okay. So, now instead of a plane, I am taking a surface, and the equation, parametric equation of the curve will be u1t, u2t. So, this is the curve C, this is the surface sigma. Okay. Now, what I will be doing, so the position vector of an arbitrary point on the curve is given by r equal to r of u1t, u2t. If you restrict the vector r onto the curve, then it will become a function of t. So, you can see r is a function of u1, u2, u1, u2 are functions of t. So, r becomes a function of t. Now, I can differentiate r with respect to t. So, differentiating the above with respect to t. So, this by chain rule, it will be del r upon del u1 into du1 upon dt plus del r upon del u2 into du2 upon dt. Del r upon del u1 is our first basic tangent vector of the surface, du1 upon dt plus r2 into du2 over dt. If you want to write it down in the summation form, you will write it like this: Ri dui over dt. I is running from 1 to 2. This is the tangent vector of the curve. Dr over dt is nothing but the tangent vector, which we already know. The only difference over here is that the curve is drawn over a surface instead of independently lying in R3. Now, here I want to explain you a summation convention. So, look here, you are summing over r, summing over I, and I is repeating itself in this expression. So, whenever you have such a situation that an index is repeating, I will not put a summation sign, I will simply write it as Ri dui over dt. So, a repeating index will be considered as a index which is running over a summation I equal to 1 to 2. So, in this case we say that I is a dummy index, I is a dummy index. This is an Einstein summation convention. Here it was easy, there are only two terms, but you may have many dummy indices in one expression, and there will be many summation signs. So, it will be difficult to get hold of them. So, we keep we have this summation convention for the sake of convenience. But you have to keep in mind all the time that whenever an index is repeating, summation is understood. Okay, so this is the tangent vector. Now, I consider a specific curve. You can think of some other curve also. So, this is dr over dt for this curve. If I consider this curve, then dr over dt will be some other tangent vector, and so on. There may be many curves. Every time the expression of the tangent will be like this. So, it is better to write this expression for differential. We can forget about t, because when you write t means you are addressing only one curve. So, in general, so in terms of differentials, we can write dr equal to Ri dui. So, which is actually R1 du1 plus R2 du2, but all the time I will write like this. Okay. But look at the left side. The left side is a linear combination of R1 and R2, and we had realized earlier that R1 and R2 are both tangent vectors of the surface. So, a linear combination of tangent vector must be a tangent vector, which you are able to see. So, this dr is a tangent vector. So, dr being a linear combination of tangent vectors, which tangent vectors? R1 and R2. Being a linear combination of tangent vector R1 R2 is a tangent vector. When I say it is a tangent vector, I mean it is a vector which lies in the tangent plane, because R1 and R2 are tangent vectors, they lie in the tangent space, tangent plane, and therefore, dr is also a tangent vector. So, it is a general tangent vector, because it is a vector which is generated by R1 and R2. So, this is an arbitrary tangent vector. So, an arbitrary tangent vector of a surface will always look like Ri dui. Okay. So, this expression is number 1 for us. When I put a t over here, you will understand that I am working on a specific curve whose parameter is t. But when I remove t, you can understand that this is an arbitrary tangent vector. It will be tangent to some curve. I am not interested in that curve. I am interested globally on a surface. So, removing t means removing curve from there, but which is there. I am not removing physically, but that is always there. Okay. So, I am interested in a general tangent vector whose expression will always be like 1. Okay. Now, what you do is, now the next problem is how to move on a surface. As I told you earlier, that when you want to go from point P to point Q, you will be going along certain curve. Okay. For some reason, I want to see what is the distance between P and Q. So, we know we will compute the length of the arc PQ. Arc PQ means the length of a segment of a curve. Okay. So, the length of an arc PQ on the surface sigma is given by surface is this all the time. So, we have a formula for finding the arc length of a curve. So, that means suppose the parametric value corresponding to P is something T P and the parametric value corresponding to Q is T Q, and this is R dot, which I am writing just dr. If you wish, you can put upon dt also when you differentiate, integrate with respect to t, and this is the length S. This is the length of the arc from P to Q. This is the length from, I have already written, note that. Okay. So, if I differentiate both sides, it will be modulus of dr, and if I square both sides, it will become ds square equal to dr dot dr. Okay. So, dr we have computed here in number 1. So, it will be summation r I dui dot summation r j duj. J is running from 1 to 2, I is also running from 1 to 2. So, there are two summation in this expression, which we are not writing because I and j both are dummy indices. So, when you will open this summation sign, you can write down r I dot r j dui duj. Okay. I is coming twice, j is also coming twice. So, there are two summation, and one more point you should keep in mind is that if you have, with regard to the summation convention, if I write down r I dui or I write down r j duj, they are same. They are same because here there is a summation which I am not writing. Here also there is a summation which we are not. So, whether index is I or j, it does not matter. Just to distinguish the two, we write down different indices here. Now, what I will be doing next, yes, that is why I put Rj over here, so that confusion does not arise. So, now denote the dot product of Ri and Rj by the symbol Gij. So, Gij means the dot product of basic tangent vectors. So, with this notation, the above thing can be written as, then we have ds square equal to Gij dui duj. Okay. Summation is there over I as well as over j. So, in the expanded form, it will look like G11 into du1 square plus G12 du1 du2 plus G21 du2 du1 plus G22 du2 square. But from this relation, from the relation above, what you get, you can see that G12 is same as G21, because dot product is always symmetric. So, I can combine the middle two terms and it will become G11 into du1 square plus 2 times G12 du1 du2 plus G22 du2 square. This is ds square. So, this is in the expanded form and this is in the compact form. Both the boxes are the same, and they are called the first fundamental form. This expression of line of the length is called the first fundamental form of the surface. So, this is called the first fundamental form. This quadratic form, this is in fact a quadratic form, because you have degree 2. So, this is a quadratic form. This quadratic form is called the first fundamental form. This quadratic form is called the first fundamental form. Or in short, we also write down F, first fundamental form of the surface. Of the surface sigma. Okay. Now, it measures the length over a surface that is always along the curve. So, you will be measuring all the time an arc, but forget about it, you are measuring a distance over a surface from one point to another point. So, the formula which enables you to measure distance over a surface is given by the first fundamental form. All right. We also call it a line element or a metric form also. There are various names, but the most popular is the first fundamental form. All right. Okay. Now, in order to study first fundamental form, u1, u2 are the parameter of the surface. They will always be there. What will determine the first fundamental form are these coefficients. So, Gij's are known as the coefficient of first fundamental form. Gij's are called the coefficient of first fundamental form, and we will study these coefficients. In fact, we will look for the properties of these coefficients so as to know more and more about the first fundamental form. तो कुछ बातें हम पहले इनके बारे में GIGs के बारे में नोट कर चुके हैं. एक तो ये कि ये GIG सिमेट्रिक है इन I and J. G12 is same as G21. So, I and J both run from 1 to 2. So, this is one of the observation that we have in mind. What next I will be doing? I will be making a matrix out of these coefficients. So, consider the matrix of coefficient. So, consider the matrix of the coefficients. Coefficient of first fundamental form. So, the matrix will look like a 2 by 2 matrix will come about G11, G12, G21 and G22. So, I can form this 2 by 2 matrix from the coefficient of first fundamental form. Since G12 and G21 are same, you can put G12 over here also, okay, since they all are always same. So, this is the matrix of GIG, okay, or in short, there is a shorter notation. You can also write this matrix as this is the matrix of GIG, okay, and its determinant, the determinant of GIJ is called the discriminant of the first fundamental form. So, it is nothing but the determinant G11, G12, G12, G22, and this we will be denoting by a symbol. The symbol for the determinant of Gij is G, and its value will be G11 into G22 minus G12 square. This is G. Okay. Now, naturally, whenever you have a matrix, you ask yourself whether this matrix is singular or non-singular. For what surfaces this Gij matrix is singular and for what it is non-singular. So, this we will be working out. So, if suppose for a minute this matrix is non-singular, then this then its inverse will exist. So, let me denote. So, let us denote the inverse of the matrix Gij by the symbol G upper Ij. Yes, this will happen only when this inverse will exist if it is non-singular. So, we are assuming it is non-singular, then we are computing G upper Ij. So, G upper Ij means the matrix whose entries are G11, G12, G21 and G22. This will be the inverse matrix, and by definition it is the inverse of this matrix G11, G12, G21, G22 inverse. This is what I am saying. Okay. So, if this is the relation between G lower Ij and G upper Ij, I can work out the relationship between the G Ij and G lower Ij. Okay. So, from the above definition, yes, from the above definition, we have G11 will be what? It will be the cofactor of G lower 11, means G22 upon the determinant. So, this is G22 upon G. G12 will be equal to minus times G21 upon G, and G21 will also be the same, because this is G12 and G21 are same, and therefore, G upper 12 is same as G upper 21. Okay. And G22, G upper 22 will be equal to G11 upon. This follows straight away from the definition. Okay. There may be other relationship also which follow from the definition directly. Okay. Okay. So, there are some other relationship between G upper Ij's and G lower Ij's. So, next what I will do is I will consider the product. G upper Ij means G11, G12, G21, G22, and I will multiply it by G lower Ij matrix, that is G11, G12, G21 and G22. Since I am assuming they are inverse of each other, then the product must be an identity matrix. So, this must be an identity matrix of order 2. So, 1 0 0 1. Now, if I multiply the first row with first column, this will give me G upper 1 1 multiplied by G lower 1 1 plus G upper 1 2 multiplied by G 2 1 equal to 1. and if you adopt the Einstein summation convention, this would also imply G1k GK1. Look, k is running from 1 to 2, okay, that is 1. Okay. And now I multiply the first row with second column, so that will give me G11 into G12 plus G12 into G22, that is 0, because this 1 2 entry over here is 0. So, that means it is G1k into GK2, k is running from 1 to 2, that is 0. Now, multiply the second row with first column to get hold of the 2 1 entry of the product. So, G21 multiplied by G11 plus G22 multiplied by G21, that is what? That is also 0, this entry is 0. So, this in the summation form will be G2k and GK1 1 1. So, that is also 0. And lastly, second row with second column. So, G21 into G12 plus G22 into G22 equal to 1. This will give me G2k GK2, that is 1. Now, if you look all these relations, what do you notice? You notice from here that when these two entries, the extreme entries, one here, answer is 1. 2 here, answer is 1. But when they are different, extreme entries 1 here, 2 here, 0, 2 here, 1 here, answer is 0. So, this will give you GIK into GKJ equal to Kronecker delta Ij. I can rewrite this thing. So, what we have got is GIK GKJ is Kronecker delta Ij, and this Kronecker delta means its value is 1 when I equal to j, its value is 0 when I is different from j. Okay. While writing all these relations, summation convention is adopted. K is a repeating index, so it is a dummy index. I and j are free index, they are not repeating, they are distinct. So, this is another relationship between G upper ij's and G lower ij's. So, these are the two types of relations that we have got between G upper ij and G lower ij's. Okay. Now, the answer to our question that what about the existence of G upper ij, whether it will exist all the time or only some of the times. Okay. Yes, exactly. So, now next I am considering the determinant of Gij to check whether it is 0 or non-zero or sometime 0, sometime non-zero. So, this we are going to see. So, now consider the determinant Gij, that is G. So, by definition G is given by the determinant G11, G12 G21, G22. Okay. So, in the determinant you will write down this as R1 dot R1, G11 is R1 dot R1, G12 is R1 dot R2, G21 is R2 dot R1 and G22 is R2 dot R2. And if you expand it, so it will be R1 dot R1 multiplied by R2 dot R2 minus R1 dot R2 or into R2 dot R1. I can write down this also as R1 dot R2, does not matter. G12, G21 are same, so I can take this liberty. Okay, put R2 dot R1 as R1 dot R2. Now look here, I can further write it down as R1 dot R1 multiplied by R2 minus R1 dot R2 multiplied by R1, and the whole thing is dot product with R2. Okay. Now look at this quantity in the bigger bracket. If I consider this as A, this as C, this as B, so this is A, this is B and this is C. So it is A cross B cross C, vector triple product of A cross B cross C. So this is R1 cross R2 cross R1 and then dot R2. So for a minute you consider this as a scalar triple product. This is one vector, this is the second vector, this is the third vector. So you can assume as if it is a scalar triple product of 3 vectors. In a scalar triple product of 3 vector, you can interchange dot and cross. So you can write down this as R1 cross R2 dot R1 cross R2. Okay. And this quantity is modulus of R1 cross R2. So G becomes equal to, in fact, square. So G is actually equal to modulus of R1 cross R2, and we know this thing that R1 cross R2 is a non-zero vector on a regular surface. In fact, it is one of the characterization of regular surfaces that this is non-zero. So if the surface is regular, then this determinant will be non-zero. In fact, it will be positive. So on a regular surface, this implies on a regular surface G is strictly positive, and therefore on a regular surface you can always find out the inverse of Gij. That is, on a regular surface, Gij, the matrix Gij is non-singular. All right. Now I can solve some problem. How much time I have taken? So I should stop, and we will take a problem in our next lecture.